Our next speaker is Rafieh Mosaheb. She's a doctoral researcher at the University of Luxembourg and is talking to us about an SoK on voting with everlasting privacy. Time's yours.
Thank you. Hello, everyone. I'm going to talk about our SoK paper titled Secure E-Voting with Everlasting Privacy, which is a joint work with Ivan, Johannes, my supervisor, and Thomas. Electronic voting is an important matter in our real life. It can have different use cases. For example, for political election, it has been used in several different countries, such as here in Switzerland. And as non-political election, it has been used in ACM. However, electronic voting on its own is not enough. We require the electronic voting to be secure. But what does secure mean? Secure means that it has to satisfy two important properties. The first one is public verifiability, which means that each voter has to be able to confirm that her vote is reflected in the final result of the election. And vote privacy means that no one has to be able to link a vote to the voter. Now the question is that how we can realize these two properties at the same time in electronic voting, which I'm going to explain next. In the common approach, we have a broadcast channel named a bulletin board that the encrypted vote of the voters appears. Then the trustees have to decrypt the encryptions, shuffle, and then publish the results on the bulletin board together with a zero-knowledge proof of correct shuffle and correct decryption. And then the auditors, which can be any third party, has to be able to check the correctness of the zero-knowledge proof and the final result of the election for the sake of verifiability. However, for privacy, it breaks down into the security of the underlying encryption scheme, which is used in the e-voting system. However, in what I explained here, we are missing something, which is long-term privacy. But why are we missing that? We have two main observations. The first observation is that anyone can see the encrypted vote of each voter. And the next thing is that the public key encryption schemes that are used in the common approach, which is mostly El-Gamal, which is known for not being quantum safe, they are just conditionally secret. So the consequence is that the adversary, which is the future adversary, which has more advanced cryptanalysis or has access to more powerful computers, for instance, quantum computers that are capable of running quantum algorithms, they can break the privacy of the voters in today's election. So that's why we require a secure electronic voting with everlasting privacy. Indeed, everlasting privacy helps us to achieve independent verifiability just based on the data that we require to achieve unconditional privacy. However, it is hard or almost impossible to achieve everlasting privacy in electronic voting setting. So in the literature, they relax this definition to practical everlasting privacy, which has an assumption on the external adversary. It actually gives a protection against the computationally unbounded adversaries that just have access to the data which is public on the bulletin board. And everlasting privacy has been studied extensively in the literature, but the state of the art is very confusing. So there are three different features that they are confusing. The first one is security properties. Some of the works, they only aim for basic security, which is verifiability and privacy. But some other works, they also aim to achieve additional features such as coercion resistancy or accountability. The next feature is threat scenario. Some of the works, they aim to achieve everlasting privacy towards just the external adversaries, while others aim for something stronger, which is everlasting privacy towards internal adversaries. And the last feature is privacy preserving techniques. Some of the works, they just use a single technique to achieve everlasting privacy. However, others, they use more techniques for this goal. But the point is that in most of the works, it is not clear that which privacy preserving technique is supposed to achieve which security property. The confusing state of the art brought up the following questions. The first question is that how do these protocols aiming to achieve everlasting privacy depend on each other? The second question is that which of these protocols are indeed a reasonable solution for everlasting privacy under realistic assumptions. The next question is that which research problems are open and which one has been solved in this area. And the last question is that is there a secure voting protocol with everlasting privacy that we can use and deploy it in the real-world elections? To answer these questions, we took the following approach. In the first step, we find all relevant existing protocols that aim to achieve everlasting privacy. Next, we classified all these protocols and we illustrated how do they depend on each other. Next, we identified the reasonable approaches under realistic assumptions that are practically efficient, they achieve public verifiability, and of course, everlasting privacy. And in the last step, we determined the solved and unsolved problems. As our first contribution, we collected 25 papers in our database that aim to achieve everlasting privacy, which shows the high interest in this topic among the researchers. Next, we classified all these 25 papers into two main groups. The first group we call identifiable ballots, and we abbreviate them as BID. It means that the ballot contains some information, for example, the voter's ID or any type of information that you can link the vote to the voter. In this approach to achieve everlasting privacy, it breaks down to the unconditional privacy of the privacy-preserving techniques that are used to tally the ballots. And in the second class, which we name anonymous ballots, and we abbreviate as BAnon, the ballot doesn't contain any information that you can link it to the voter. Therefore, everlasting privacy breaks down to the unconditional anonymity of the ballot submission channel that the voters are using. And we argue that the general approach in the BID class is superior to the general approach in the BAnon class. Because there is a significant gap between the unconditionally private channels, which is used in the first class, and the unconditionally anonymous channel, which is used in the second one. The point is that to realize these two channels, actually both of these channels, they do not exist in the public key setting. So to realize them, we can get closer in reality to the first one than to the second one. The point is that to realize the first one, we can use post-quantum TLS, which has no effort on the voter side. But to realize the second one, every voter has to have access to Tor, not every, but the majority of the voters. But this is not a realistic assumption to make in e-voting. And the next reason is that we are aware of some organizations and intelligence services that they gather metadata during the election and they observe the network traffic. And whoever that has access to this data in the future, they can break the anonymity of the channel, but purely based on this metadata, the privacy of the channel still holds. So with these two reasons, we claim that this group is superior to the other one. The next contribution is our conclusion table. We have all these 25 papers, all these 25 protocols here with their corresponding subgroups. And we also have their distinguishing features. And we mentioned that for achieving some properties such as public verifiability, everlasting privacy, or any other additional properties that they aimed for, what is the underlying trust assumption that you can see in these three columns? And lastly, their practical limitations if it exists. During our analysis, we figured out that reference number 22, Quellier et al., and the following works based on that, they achieved it's a reasonable solution under realistic assumptions for everlasting privacy problem. However, we also figured out that reference number 11, Buchmann et al., and the following works based on that, they didn't achieve everlasting privacy based on the assumptions that they made. To summarize, I would like to mention the solved and open problems. Regarding the solved problems, we distinguish between two different ballot types. The first one is simple ballot type, which means that each voter has to vote only for one candidate, and we also have the arbitrary ballot types, which means that the voters can rank the candidates. For the first one, for the simple ballot types, the solution exists in the superior class, but for the arbitrary ballot types, we have solutions in both of the classes. By solution, I mean reasonable solution under realistic assumptions. And regarding the open problems, actually, deep cryptographic analysis of the reasonable approaches that we have on the left-hand side exists, but protocol level analysis or the formal verification of them do not exist, so it's still an open problem. In the B-anon class, we have Belenius protocol, reference number 3, which is a popular electronic voting protocol that you can use at the moment. However, in the superior class BID, we don't have a ready-to-use electronic voting system. The third open problem is that we require weaker trust for arbitrary ballot types. In the suggestions that we have in arbitrary ballot type, the assumption is that there is a full trust on the election authority. And also in none of the reasonable approaches, they achieve receipt freeness. This concludes my talk, and thank you for listening.
Thank you very much, Rafieh. So one question I had, it relates to just a general property of these voting systems. So you mentioned properties you are trying, or these systems try to provide are both vote privacy and public verifiability. Many real-world voting systems also try to enforce that every individual only votes once. Is this a property that's implied by vote verifiability, or is it actually, is it maybe a difficult property to achieve because of privacy, or is it just axiomatically assumed? Is this a property that's considered?
Actually, when they force you to just vote once, it's the question was that you can just vote one or more than one, because there is an approach, we call it revoting, that's to prevent coercion resistance. It means that to prevent someone to force you vote in a specific way, so they allow you to revote just in case, to somehow revoke your ballot in case someone forced you to cast it.
I see. So some of these systems do have single vote or revoting. It's just it depends on the system.
Yes, it depends on what property they care more to achieve, but I mean, if there is a protocol that it's not verifiable or it doesn't have privacy, it doesn't worth it. So it has to have these properties to be secure, and in case that they want additional properties such as coercion resistance, then they have to take some different approaches.
Great. Are there any other questions for Rafieh? Okay, well, great. Let's thank the speaker again.